Good afternoon, everyone. So my name is Ben Hall, and for the last 3 years, I've been letting anyone on the internet run potentially malicious code on my servers. And this is a story about how I managed to do that and how I managed to keep ourselves secure and utilize containers, keep everything nicely contained. And the reason why I let anyone run any code they want on my servers is because I'm the founder of Katacoda. Katacoda is an interactive learning platform for software developers. And so we teach people how to use Docker, Kubernetes, and many of the other cloud-native tooling that you're going to hear about today and tomorrow, such as the Istio, Harbor, and all of the other foundation projects. We work closely with different companies, such as Red Hat, who have learned at OpenShift.com, where they describe how you can use their OpenShift platform to solve many of your problems. And we're embedded into the Kubernetes website at Kubernetes.io. So you can try Minikube, you can have a safe place to experiment. You don't have to worry about breaking your local laptop or slow internet connections, etc. It can all be done in the browser without any downloads or configuration. Now, as you would imagine, when people see this terminal window, they've never been asked for a login, they've never been asked for an email address, they don't have to enter credit card details, and so they like to explore. And so they'll kind of poke around and they'll see that they're root, because we want people to be able to learn to the full potential. We don't want to restrict what they can do. And so they can install different packages, and obviously they can then try and delete everything. And that is always beautiful when people delete anything, because it's just this wall of text where Linux kind of lets you delete certain things and then says, no, you can't delete processes that way, don't be silly. And like from a viewpoint of me, it's like, great. You successfully managed to destroy your session, but you haven't managed to damage Katacoda. And that's because we are building on top of the container technology. And we'll get more into that in a moment. But we kind of progress further, and people try and explore more interesting aspects, such as slowing down Google by causing DDoS attacks and getting really excited when the Google response time is slightly slower. Now, obviously, this doesn't quite work with ping. Google can cope with that. However, we do see more glamorous networking type attacks happening on our system. And so what we're going to talk about today is how we look and manage containers and the container security aspect. So we're going to have a quick refresher about Container Security 101 to make sure that we're all on the same level, indicate how certain features of Katacoda are being utilized, or certain features we're using. We're going to look at then different types of attacks and different ways that people are attempting to exploit Katacoda. So cryptocurrency mining is a popular one, and we'll look at how that's being coped with. And then we'll look at more kind of exploits. So how they're trying to exploit the kernel, how they're trying to attack our host, and then how are they trying to perform other networking and related attacks to gain access to Katacoda infrastructure or other people's. So when they have this terminal and they try and delete everything, how do we make sure that that isn't affecting Katacoda and that isn't having an impact on other users within our system? And thankfully, most of this comes for free because of the features which we have inside of Docker and container technology. And so as a quick refresher, we've kind of got these core technologies. We can allow users to run as non-root if we wanted to by setting the flag in either the Docker file or when we launch the container. Now, this isn't quite relevant for us because we want people to be able to install packages. We want people to have control in a live environment. But obviously, in a realistic production environment, you would never need to run apt-get install or install additional packages, because that would be done in your beautiful continuous integration pipeline. And so instead, you can set a user as non-root and become more secure. Now, a feature which is more beneficial is user namespaces. So this is how you can separate what is considered root and the root privileged user on the host machine to what is considered the root user inside of a container. And so by having this isolation, we add if a person did manage to break out the container, they wouldn't have root permissions on the host. Instead, there would still be a low privileged user on the host. The container, however, would be able to install and package everything up. We have copy on write technology. So this is how we get some file isolation. So when everyone deletes files within their containerized system or that container environment, that's not actually deleting the file on the raw disk. It's not deleting that base images. Instead, it's just adding the pointers into the copy on write to indicate from the file system viewpoint that the file no longer exists. But actually, because we're using images and we've got that base image, the underlying file isn't never touched. And so people can delete whatever they would like. We then need to start worrying about how do we restrict people? How do we limit how much access and how much capabilities they can utilize in the environment? We can't just give away infinite resources for free, so we need to restrict it somehow. And so the first way we do that is with C groups. C groups limit things like how much memory can a process access. So we want to limit everyone to a gigabyte of memory, then we can limit that process using C groups. We can limit how much CPU it can access by shares, and so making sure that it can't overload a system, making sure that it has equal share of the resources available. Now, this is somewhat problematic. It's not ideal, and we discuss how that works later, but there are these resources in place. And we can control other things like disk I/O, how quickly can you write to disk, how quickly can you write to the network, and other kind of restrictions. But they're not hard limits, and this introduces problems for us. And we'll discuss those in a minute. We have namespaces, so what can a user see? So when a user goes on to a containerized process and go like, hey, what's running on the system? They will only see the processes which belong to that containerized process. And that makes sure that they can't interact or interfere with anything else running on the system. They also have their own networking and networking namespace, so they can't interact and interfere with other networking options running in someone else's session, and so we get these nice isolated pods all around our system. There's additional kernel flags to block gaining additional privileges. This gives us some levels of protection, making sure that they can't gain additional privileges if they wanted to. And then we have the three features at the bottom: ThreatComp, AppArmor, and capabilities. And these are probably the most important security features for us, because this limits all of the dangerous interactions and dangerous system calls that a user may be able to make. For example, we can block people mounting the disk of the host from within inside of the container, so that they can't get access to the actual disk. We can block them being able to install kernel modules, because we don't want them to have access to that kind of level. Change things like host name, system clocks, all of these kind of core functionalities get disabled with a combination of ThreatComp, AppArmor, and capabilities. And this all comes out of the box for free, right? All of this comes out of the box for free with Docker, as long as you've got it configured correctly. And so we can build on that, and we can take advantage of these functionalities. But everyone's threat model is different. So for Katacoda, we have a very particular threat, i.e. we have already allowed everyone to hack us by giving them complete open access to the system. But if you're inside of an organization, it may be different. You may have different attack vectors and different things. And so I recommend everyone to take into account what their threat model looks like. As I was saying, Katacoda is very explicit, but you'll see the Katacoda style of experience in many different places now. If you're using one of the cloud platforms like Azure, then it would have the Cloud Shell. You've got the Google Cloud Shell, and all of the IDEs nowadays, or the web-based IDEs nowadays, have this interactive terminal where you can run all of your processes directly in the browser without needing to download or install anything. And other hosted CI/CD platforms, Heroku, etc. But it goes beyond this, because all of these platforms are exactly the same as if you accidentally left your Kubernetes dashboard open to the entire world, or left a port open and allowed everyone access to your systems, which unfortunately has been in the news fairly recently. And so Tesla was a recent one where they exposed their Kubernetes dashboard to the outside world, and as such, people could automate that, script the attacks, and as such, in this case, steal confidential company info, and then run cryptocurrency mining on top of it. And so basically, this is what the talk is going to discuss. What happens when you've accidentally been exploited, when someone has gained access to your system? How can you impact the blast radius? And how can you impact how much control they have of your system? And so let's look at cryptocurrency mining to start with. Now, cryptocurrency mining is quite simple to detect in its nature. When someone starts, you see a nice spike on your CPU. Everything goes to 100%, and it will sit there happily until the process is shut down. And now the problem is that with Katacoda, we also run machine learning. We want people to be experimenting with TensorFlow, Kubeflow, etc. And actually, the traffic patterns and the behavior is very similar. Like, it's very hard to detect what's a legitimate cryptocurrency, and not legitimate cryptocurrency, compared to a legitimate machine learning process, because they want to do the same thing. They want to take over all of the resources and run everything as quickly as possible. And so now that we start getting into like, how can we start detecting legitimate workloads on our system compared to non-legitimate exploited attacks? And so now let's look at how we do that a bit more closely. Now, as I was saying, if you do something like leave your port open, you'll get people scanning the internet trying to find these loopholes, trying to find these gaps in systems that they can use to exploit. So this was an accidental honeypot, which I put on the internet. I accidentally left the Docker port open, and someone kindly sent me an email saying, like, you probably don't want to do that. It's pretty scary because I wasn't sure how they found the email address until they pointed out in your SSH file and your authorized keys, you have your email. So it's like, excellent. That's concerning. And this is what everyone's doing. But attacks can be a little bit more subtle than that. So this is an attack where people were using cryptocurrency as part of images inside of the Docker hub. And this is one of the issues which got reported to Docker. It's slightly concerning that it's still open because there's not really that much Docker can do. But the case was, it was a legitimate image. It had a legitimate use case of performing memory tests of the system, making sure that all of the memory was valid. And so the problem with that is memory tests take quite a long time to run by their very nature. So this was happy, it was doing its job, but in the background, it also had cryptocurrency mining running. And so it would not only be utilizing all of your memory, it would also be utilizing all of your CPU without you being aware of it. And there's lots of these other attacks, which is why we should never download a random image of the Docker Hub and run it in production, because we do not know what it's doing in the background. We don't know where it's sending our data or how it's utilizing our system. And then it got me wondering, like, if I'm running a cryptocurrency mining and I find the coin, which is great, but then how do I get it back into my wallet? Like, how does that process actually work? And so I started exploring, and there's all these miner pools. And so the idea of a miner pool is no matter how small of the resources you share, you can get a slice of the payout. And so even if you only manage to run the cryptocurrency mining for 10 minutes, you will still get a share of the overall miner pool when a coin has been discovered. And there's lots of these different platforms which people are utilizing in order to be able to gain access and gain shares of this coin once it's been discovered on one of these many different systems which are all connected. And this is how the Tesla attack worked. So they hid their IP addresses from Cloudflare, so you couldn't actually easily block the incoming traffic, even if you wanted to. And then they were using unlisted and kind of private-ish miner pools. So you couldn't even just blacklist all of the IP addresses in the system to make it, to restrict it, which is problematic. And it's more than just cryptocurrency. So we have people using Katacoda as a render farm, which is definitely not the purpose of what we were trying to achieve. And so again, very similar to cryptocurrency mining, they would connect to this render farm pool. It would pull down all of these assets, render them, and then upload them again. And this was even more problematic because now not only are they burning through CPU, they're also burning through data. And so they would be downloading these gigabytes of assets to then burn through the CPU to then upload a gigabyte of assets out the other side, which was unfortunate. And also BitTorrent. BitTorrent's still around, it still exists, it's never going to go away. And obviously people attempt to use Katacoda as a feeder and feed traffic on top of it. So how do we solve all of these problems with networking and people trying to misuse Katacoda in undesigned ways? So as I mentioned at the beginning, we have C groups. We have ways to limit isolation and limit how much a user can do within the platform. But this doesn't quite take into account So we can restrict memory. Great. So we can say that you can only access a gigabyte of memory. But we can't restrict CPU, which is particularly a problem when we're looking at very CPU-bound attack vectors like cryptocurrency or 3D rendering. And the reason we can't do that is because it's a share. We can say that it's a weight of how much CPU a process is allowed to access. And so if nothing else is running on that box, it has all of the shares available because there's nothing else interrupting it and nothing else requesting access. If something comes along with a higher privilege, then of course it will get interrupted and it will take the higher privilege process will have access to the CPU it requires. But that doesn't mean that any leftover CPUs is still being utilized, hence why when the attack starts, all of the CPU spikes to 100%, no matter how we've configured these CPU shares. In terms of networking, we can't control how much data a process is allowed to use. We can't tell Docker, hey, only allow this person to upload a gigabyte of data and then cut them off from the network. We don't have those APIs being exposed within the system. Now, fortunately, with Kubernetes and the container networking interface, they are introducing traffic shaping. So at the lowest level, we will have APIs within Kubernetes where we can control how much a pod is allowed to use of the network. How quickly will it be allowed to write to disk, write to the network, and how quickly will it be able to upload or download data. And this will give us some control and some assurances about how our applications are allowed to behave on the system. But even with all of these things in place, people will find additional ways to be hidden. So this was kindly donated by someone on Katacoda. By the virtue of them running it, I deemed it donated. And you can see at the top, it's checking to see how many CPUs we have access to. And it's like, if it's below 4, that generally means we assume we're running on a VPS or some kind of cloud system which have been accessed. And so instead of taking over the entire box, always run at 75% to try and be below all of the alerting and all of the radars, and so that we don't get email alerts saying that something has gone wrong in our box. And so now we need to take into account that when we've got this huge cluster of machines, we can't rely on the fact that we're testing for CPU spiking to 100% to be able to block these attacks. We need to actually be monitoring what things are running on our system. And so the two main ways that we are defending ourselves and we're restricting these kind of attacks. One is kill long-running processes, and the other is block what networking options are allowed to be done within our system. So long-running processes is, as you would imagine, very forceful. It's pretty much kill everything which is running for over an hour or for a particular point of time. And this is what serverless technologies are doing all the time. Like when you go to AWS Lambda or the equivalent here, you would only be allowed to run serverless for 5 minutes or 15 minutes, depending on how it's configured, and then it automatically gets shut down. And so this is a similar process which we're taking. And we've already been encouraged this with VMs and containers. Like we don't want these long-running VMs for just maintenance reasons. They'll get out of date, they'll become a snowflake, i.e. they'll be unique, and we want to make sure that they're being automated and refreshed. And so we already have this habit of recycling the containers and VMs every now and again. And so we just introduced that for environment sessions too. And this is good hygiene practices. If a container has been changed or modified, by recycling it and killing it automatically, then we are introducing an additional level of protection. Something very easy to do now with Kubernetes, which will manage that process and roll out for us without us losing traffic or interrupting the users. The next one is a little bit more interesting. It's about how do we block and restrict certain types of bad traffic and certain types of bad user behavior. And one of the approaches is IPtables. Everyone knows and loves IPtables, which isn't quite true. No one knows IPtables really, and definitely no one loves IPtables, but they are extremely powerful, and they do give you a very low-level way of controlling your network. And so an example, we can say like port 25 on the outbound of the traffic isn't allowed. So no one can connect to a mail server on Katacoda and start using us to spam people's email. Instead, we've blocked port 25, which is great. But the problem is that this doesn't quite work with Docker. The way that Docker's configured its IP tables is it interjects itself at interesting points, like really early on in the process. It then has its own filtering mechanisms going down the chain. And so it makes it very hard to gain access and compete with Docker about who has got the filtering capabilities within the system. It is possible. You need to inject yourself before Docker, but it's something to keep in mind that you can't just apply IP tables and expect them to work because Docker will just ignore them by default. A more interesting capability is using the packet filter, BSD packet filter. Now this gives us much more control, and it allows us to inject code into the kernel which can inspect and check every single packet going through our network. And because it's at the kernel level, it's very low level and has a very low overhead on all of our traffic, and gives us the capability that we can block things like DDoS attacks or port scans or other things happening within our network. And this is how some companies like Cloudflare block their global attacks with DDoS, because they have these packet filters injected into the kernel, which is inspecting everything which is happening. But they're not very accessible. It's not very easy to write these packet filter programs. A much more acceptable and approachable way is using a service mesh. So something like a network policy in Kubernetes or Istio, which everyone's talking about. For those who aren't familiar, with having something like Istio in place, all of the traffic in our system, we can filter, we can add restrictions to make sure that only certain services can talk to each other, so that we don't open up our entire platform to everyone else if an exploit did happen. And we can also restrict all of the outbound. So all of the egress outbound traffic in Istio is blocked by default. And this is good practice by design. Like, why do we have containers and pods talking to the outside world when they should be completely isolated, sandboxed, and they shouldn't go off to things like apt-get to do updates? Instead, we don't need that happen. Instead, we can just keep everything closed and only whitelist the APIs that we do need to talk to and which do need access to the outside world. And then if someone does manage to break into a system, they wouldn't have access to the whole world. Instead, they'd only have access to other things, and we can keep that attack contained. But fundamentally, it's a game of cat and mouse. Like, there's always going to be new attacks, there's always going to be new exploits, and we're kind of watching, monitoring, and keeping things on top of it. And this is where we start seeing other types of attacks, and the main one being piggybacks, like people using Katacoda in order to launch additional attacks against ourselves or against other people. So I'll start with talking about host-level attacks. Now, this is where someone's gained access to your system and are now attacking the system which that pod or that container is running on. And the biggest problem is when people decide to run everything as a privileged container. So when you do Docker run, you set that privilege flag, and basically it removes all of the security capabilities that Docker has enabled by default. It makes sure that everything runs, but as such, we have no security. And this is very easy from an attack vector to then gain access to the host. You can ask the kernel information about the system, i.e., what disks do I have in the host? And Docker will kindly tell you things like dev VDA1, that exists. Because you're privileged, you can use mount. So you can mount a disk into a temporary folder within the container, and then you can just navigate it around. Because you are running at privilege, you're running as root, you can gain access to all the files, you can gain access to things like authorized keys, write to your own authorized keys, and then you have access to the host. You can log in, you can delete their key if you wanted to and kick them out of the system. Fundamentally, you have complete control, and it takes roughly 30 seconds to gain access. So privileged containers, extremely bad behavior. But by default, we have things in place which stop these kind of attacks. We have the things which I mentioned at the beginning, the SEPCOM, AppArmor, the capabilities. which restrict things like mounting so that we can't mount the disk, and so we can only access things within our containers. And this also gives us some more control. So if you run strace on a process, you'll see all of the system calls that process is being made. And as such, setcomp will then allow you or disallow you to which system calls you're meant to be, which you're allowed to call. So in this case, we're allowing open, we're allowing read, but if people change the file mod, do a chmod on the file, then that's going to be blocked, and we can restrict how much control people have. And this is good because this allows us to restrict system calls which are potentially malicious and potentially dangerous. One of the very early Docker escapes, way back in 2014, was using a system call. It's basically looping over every single inode file handle in the system. It was trying to get the file name, and then once it had found a file which it was looking for, in this case the passwords file, it would just open the file given that handle, because it found every single possible handle, and so it found the one it was looking for. And so it gained access to every single file on the host machine by the very nature of inodes. And so the way Docker solved this solution, one of many ways, was to disable the capabilities, update the setcomp profile, and make it much more strict and have a better whitelist by default, which has helped us all, because now, by default, all of these dangerous or potentially dangerous system calls have been blocked. But we can start to discover things by the very nature of containerized systems. The container is still running against a shared kernel. Like, everything on our system is still talking to the same thing, even when they're on different containers. And so we can ask about things like uptime, what version of the kernel is running, and like what CPU or what disks are on the system. And this allows us to find potentially interesting attack vectors within the platform which we've got access to. So this is the Azure portal. And so we can ask, like, what CPUs do I have access to? What CPUs is this container running on? And it kindly now reports all of the bugs that have been fixed. It reports that it doesn't have Meltdown, doesn't have Spectre. Great, Microsoft is secure. But at the flip side, if we ask any other system and it doesn't report this information, we know that they are vulnerable to these attack vectors. And we have Meltdown and Spectre potentially available to us. We can see information about where it's running. So you can ask a process what C groups have been applied. And so in this case, Docker, like Katacoda and Docker, can report that you're running inside of a container. And if you're running inside Kubernetes, like which Azure does, it will say you're running kpods. Great, I know that I'm in the world of Kubernetes. And so now I can start looking at potential Kubernetes exploits to find ways into the system. So I know information about the context, like have they accidentally left a service account token on the environment? Do they have RBAC enabled? And have everything been restricted? Because I know my context, I know potential attack vectors. But I also know about how that process has been deployed. So in this case, this is me connecting to Azure and instantly I go and open up the portal. But it already says that that instance, that process has been running for the last 46 minutes. And so that means like either they have a pre-warmed set of VMs running that you just connected to, or it's potentially a shared VM. We can look at the kernel and see if it's running anything old and potentially vulnerable. In this case, Microsoft aren't, which is great. But we can look at things like the file, what file system options are available and what disks are available. And we can write to certain locations, like test, like the temp folder. And so if we can write to the temp folder, that means that we could potentially fill the disk. If it is a shared VM, then that's going to interrupt everyone else. And that's going to interfere and interact. No one else will be allowed to use the system. And this gets even more dangerous because we can add quotas, like device mapper, XFS can limit and have a quota about how much disk space you're allowed to use. But we can bypass all of that if we're using root and we have XCD hosts. Because of how this is mapped into the system, it's actually mapped outside of the quota, outside of the overlay storage. And so we can just write to that and it will fill up the disk and bypass everything else. Credit where credit due. This is one of the things which Red Hat have solved and fixed with Podman. And so if you look and try and perform the same attack vector with Podman or a container running on Podman, which is Red Hat's new container runtime, then you'll see everything which is potentially could be filled is now stored as tempfs. And so instead of XD hosts having access to all of the disk, it only has access to 100 meg, which is much more sensible as a default option. And finally, we have things like fork bombs. And this is a great bit of bash scripting. We create a new bash function called colon. The body of that is calling the function colon, piping the output to a function called colon, and then releasing control. After the function has been defined, it calls a function called colon. The effect is a huge resource consumption of your system. The system load goes up to 4,000. You have 7,000 processes running, and that is the last you'll see of that box until you do a physical hard reboot, because there's no processes and no resources left on the system. And this is just frustrating. There's literally no purpose to it apart from causing disruption. And previously, when Docker was first released, there wasn't a fix. But fortunately now, Docker worked hard with the Linux kernel team. They introduced a new flag called PID limit. And so now we can restrict how many processes people can fork and how many processes people can launch. So in this case, they would only ever allow 512 processes, and we can restrict the attack approach. So the final one is how people misuse networks and how people misuse our networks. And this is pretty clear when you see, again, people launching DDoS attacks and seeing huge spikes in the network. And when that happens, people port scanning, like from the matrix, and seeing what ports are available, both internally to Katacoda, but also externally, trying to find other loopholes in other systems and using Katacoda as a way to potentially do that. And this is extremely difficult to control. Like, there's no nice APIs within Kubernetes which you can say, please don't allow a DDoS attack, because it just doesn't have that capabilities in place. So instead, this is where we have to fall back to things like the Berkeley packet filter and have that very low-level, fine-grained control, which does an inspection on every single packet through our system to see whether it's potentially allowed or not. But what about internal attacks? Like, we have potentially attacking the Kubernetes cluster via the service account, service tokens that have been left in a pod. And this is something which has now been disabled with RBAC, and so by default, we're much more secure. But it's something that you need to make sure that you have configured and have enabled on your system. And again, this can all be solved with doing things like network policies, restricting how much scope a pod, how much scope a container has. And Kubernetes has great APIs to support this. So in this case, restricting who has access to our API. And also restricting who has access to the outbound internet. So basically, we can apply this network policy, and everything within the default namespace now is not allowed to talk to the outside world. So even if we did somehow manage to, attacker managed to find an exploit, they wouldn't be able to talk to the outside, they wouldn't be able to launch DDoS or cryptocurrency mining because the network is restricted. And this is what Istio is doing. This is how Istio is protecting our systems, and why Istio is a great security feature to have and start building upon. But all of this is irrelevant if we don't have visibility. We need visibility in our systems to ensure that people are aware that people are attacking us, but also aware of what attacks they're potentially launching. And so a great way to solve this is Sysdig and Falco. Falco has recently donated to the CNCF as a sandbox project. And what it does is it monitors everything within your system, everything which is happening, and then raises alerts when things are potentially abnormal, things which shouldn't be occurring, like a bash prompt running, or something changing file permissions, something outside a normal boundary, or the process starts to talk into certain ports that it shouldn't be. Like, is this pod now being exploited by a cryptocurrency mining solution? And Falco can alert you on this, post it into a Slack channel, and then you can go and investigate and gain visibility into your security process. And this is a great way to protect yourselves. So in summary, like, are containers secure? Well, fundamentally, yes. If you are following the best practices, if you are following all of the right guidelines, containers have a huge amount of security built in. But like with everything, there are gaps. There are gaps in the system which, like, if you don't configure correctly, you may be vulnerable to. So hopefully things like the networking I discussed will give you insights in how to protect it. But at the end of the day, nothing is secure. Like, VMs aren't a secure approach. This is a beautiful attack, which the attackers could break out of a VM just by attacking the floppy disk driver, which is exactly what you need when you're running a huge cloud-based platform. So it's dangerous, but like, this is what we've been doing for the last 3 years in Katacoda, but as a community and as a technology community, we've been doing this for the last 20 years. So we know security is always a risk. We just need to make sure that we're applying the things we need to make sure that we're as secure as possible at this point in time. So here are some quick wins I'd recommend. If you can, don't run as root. Sadly, this isn't the case for Katacoda. We want that, but normal everyday production systems shouldn't be running processes as root. If you can, make the file system read-only. Make sure that no one can actually write to disk, because then if they can't write to disk, they can't download additional binaries, which means they can't launch them in the first place. Keeps you much more secure. If you can, again, block egress. Block all of the outbound traffic, because why do you need it if you've got a good CI process and your image is being built and then deployed? It should never change, which means it should never need to talk to the outside world, apart from a few certain APIs. And that's where things like network policies and a service mesh and Istio can help control that. It can help give you those flexibilities and the APIs to make that easy to manage without having to resort to IPtables. But fundamentally, you need visibility. You need to create visibility to see what's happening within your system and see any potential attacks which may be happening, because otherwise you're just blind to what's happening in the system. And with that, I hope you gain something. Thank you very much for listening. If you have any questions, please always tweet me or email me at katacoda.com and go explore and have fun on the platform and see what you can learn. Thank you.